Alright, chapter 6. We're going to look at some more applications of integration. We're going to look more at areas under curves, and we're going to look at volumes, and then we're going to look at work and average values. Suppose instead of trying to find the area under a curve, you want to find the area between two curves. Well, first, if you graph it, you get something that looks like this, right? So this region right here is what we're talking about. And so what we're going to do is, if you can find the area of a typical rectangle, these are these rectangles that you're going to add up, right? And then you're going to form a Riemann sum. You can take a limit as n goes to infinity to form a definite integral. We're not going to go through all that stuff, but at least we're going to look at a typical rectangle. If you can tell me what the area of that is, then we can write the definite integral that way. We need to know the limits of integration, though, so we need to know where they cross. If you set y1 equal to y2, you get that x equals x squared minus 2x. So you solve this quadratic by factoring, and you get 0 and 3. Makes sense? You're going to be adding these areas up from 0 to 3. Now, what is the area of this? It's going to be the top. It's always, when you have a situation where you have a vertical rectangle, it's the height of the rectangle times the width. The width is delta x, so it's going to be a dx integration. And the height of this rectangle is going to be the top function minus the bottom, isn't it? That would be this distance right here. So the top function is this. You got to graph it correctly. So it's going to be x. I could say x sub I minus x sub I squared minus 2x sub I. That would be a typical this distance right here. Anyway, after adding those up and taking the limit as n goes to infinity, you can see where the definite integral comes from. This integrand here would be the height. It would be y at top minus y bottom. The delta x becomes your dx. That's the width of the typical rectangle. Limits of integration are 0 to 3. That's how it works. The integration usually isn't the hard part. If you combine like terms and integrate, let's see, you get 3x squared over 2 minus x cubed over 3. When you plug in 3 on the top and 0 on the bottom, I get 9/2. You can check me on that. Let's do some more. Find the area between the curves x equals y and x equals y squared. So let's graph the region. Look, it looks kind of like this. Since we're looking in the first quadrant here, you could solve this for y. You get y equals plus or minus the square root of x, but isn't it true in the first quadrant? This would be y equal the positive square root, as long as you don't dip down here. So you could solve this for y. Now, the area of this typical rectangle is going to be, since it's a vertical rectangle, the width is going to be delta x. By the way, let's first find the limits of integration. You set these two equal to each other. You square both sides, and you factor again, you get 0 to 1. That seems reasonable. X goes from 0 to x equals 1. Now, the height of the rectangle is always y sub top minus y sub bottom. So it's the square root of x minus x. That's where that comes from. This is the height of the typical rectangle times the width added up. That's where we get the definite integral. It does help to know where the idea of Riemann sums. It helps you understand definite integrals better, doesn't it? The integration isn't too hard. You get x to the 1/2, you get x to the 3/2 divided by 3/2, so times 2/3, minus x squared over 2, evaluate between 0 and 1, I get 1/6. Now let me tell you another way to do it. You could also use a dy integration, and there's some cases where you have to do this. Instead of solving for y, let's just leave it as x. And let's draw our rectangle this way. Horizontal rectangle. So what would the area of this typical rectangle be? Well, the width is not delta x anymore. The width of the rectangle is actually delta y. This is going to be a dy integration. And the way you would find the height of the rectangle would be x sub right, the right x coordinate minus the left x coordinate, x sub r minus x sub l.
So in other words, it becomes y minus y squared.
That's where that comes from. So there are some. So you get used to being able to integrate with respect to y as well, especially when you can't solve the equations for y. So it's always right minus left and top minus bottom. Did we find the limits of integration? Oh, you can see if you set them equal to each other, it's y equals 0 to y equals 1. So we're literally adding these up along the y-axis instead of the x-axis. Anyway, integration isn't too hard. Hey, the answer's the same. That's nice. Better be, since it's the same problem. So I was talking about this. Here's an example of what I'm talking about. There are times when you may have to use a dy integration, or at least it's easier. Find the area between the curves x equals y and x equals 2 minus y squared. The area, the region looks kind of like this, so it would be kind of messy to try to do a vertical rectangle here, because over here, for example, it would hit the same function twice, and plus you'd have to break it up into two separate integrals. It would be a lot messier. This is much easier. Anyway, so if it's a dy integration, you got to find where they cross. You got to find this y coordinate and this y coordinate. If you set so you'd set x1 equal x2, that means y equals 2 minus y squared. And when you solve this for y, you end up with y squared plus y minus 2 equals 0. Factor it, you get y equals negative 2 or y equals 1. That seems reasonable. Y equals negative 2 to y equals 1. That's what the graph looks like. So remember, if it's a horizontal rectangle, it's always going to be x sub r minus x sub l times delta y. The right one is 2 minus y squared. That's why we get this. X sub right minus x sub left. This is your right x coordinate. This is your left x coordinate. And the limits of integration from negative 2 to 1, dy. Anyway, like I said, the integration is not the hard part. It's setting it up. So when you integrate, you get this, and you evaluate at 1 minus evaluating at negative 2, and you simplify, I get 9/2. Why don't you try this one? See if you can do this one. Go ahead and hit the pause button. See if you can find the area between the curves y equals x and y equals x to the third. Okay, certainly drawing a picture is a good idea. Did you remember that there's a region here too? It says the area between the curves. There's actually two regions to consider. I think it'd be very easy to forget the fact that there's two of these. Now it would be okay to use a symmetric argument. You could definitely do that, and you could say that from the graph it's clear. If you could find this area here and multiply by 2, that's totally fine. You could do that. But this is the total region we're talking about. Vertical rectangles make sense, so it's going to be a dx integration because your delta x, you're partitioning along the x-axis, and the height of this typical rectangle would be the top function minus the bottom one, so it'd be x minus x cubed. And I did that. I multiplied by 2 to take care of this one too. And you can see where these cross. They cross at 0, 0, and 1, 1. That's not too hard to see. So from x equals 0 to x equals 1. The integration isn't too hard. Final answer is 1/2. Okay, let's do a couple more. Actually, what time for one more? Why don't you try this one? This is a hard one, I think. See if you can do this one. Find the area between the curves x equals y squared and x equals 1 minus y squared. Okay, you draw a picture. I think it's safe to say that it would be easier to draw your rectangles horizontally. So that means it's going to be a dy integration. Why is it a dy integration? Because your delta y, the width of the rectangle, is along the y-axis, isn't it? Okay, so what are the limits of integration? Well, that's kind of hard. You'd set these two functions equal to each other, set x1 equal to x2, set this equal to this, so that means y squared equals 1 minus y squared. And when you solve that, you get 2y squared equals 1, you solve for y plus or minus, right? Y is plus or minus 1 over the square root of 2. That seems reasonable. Again, I'm going to use a symmetric argument here. I'm going to say that this area is clearly going to be half of this area, so in that case you just have to go from 0 to 1 over square root of 2, you see? I'm going to look at it like this. Anyway, and it's going to be x sub right minus x sub left. So it simplifies to this, and when you integrate you get this, and then you evaluate it. My final answer is 2 2 radical 2 over 3. Okay, we'll see you next time. Bye-bye.